Hello everyone, welcome back to the channel Code with AKJ. Today is day 44 of solving GeeksforGeeks problem of the day, and today's question is two smallest in every subarray. So the question says given an array of integers ARR, the task is to find and return the maximum sum of the smallest and second smallest element among all the possible subarrays of size greater than 1. If it is not possible, then return 1. So give an example here. The array consists of values 4, 3, 1, 5, 6, and the subarrays of this particular given array would be 4, 3, 4, 3, 1, 4, 3, 1, 5, 4, 3, 1, 5, 6, and so on and so forth. So we need to find the smallest and second smallest values out of each subarray, and we need to take the sum of it. And finally, after all the sums we'll get after finding these subarrays, we need to take the maximum sum out of it. So here the task is simple. We have given an array and we need to find the subarrays of these array, and we need to find the maximum sum of the smallest and second smallest element. So they are expecting us to complete this problem in O of n time complexity, and space complexity should be O of 1. So the initial thoughts would be to generate all the subarrays of this given array, and we'll find the smallest and second smallest element, and we'll calculate the sum, and we'll keep a track of these sums to get the maximum sum out of it. So based on this explanation, we can easily find out the brute force solution is to create all the subarrays, and parallelly we'll find out the smallest and second smallest element. We'll calculate the sum of these two elements, and we'll keep track of this sum to get our maximum sum out of all these subarrays sums. So I think there's no need to dry run this particular approach. The explanation is clear. Let's try to move on to the code directly. So the code here starts with taking the size of the array. We'll run a loop over this array to generate all the possible subarrays. J will run from I to n, and we'll take two variables which would be int max initially, that is smallest and second smallest. We'll again loop over these subarrays to find the smallest and second smallest element, where k starts from I to j. So we'll check if this particular current element is smaller than the smallest element. If it is, we'll update the second smallest element with the smallest, and smallest with the current value, array of k. Else if we'll try to check for the second smallest element, we'll compare it with second smallest variable, and if the current element is smaller than the second smallest element, we'll update our second smallest variable. So in this way we'll get our smallest and second smallest element while calculating the subarray as well. And finally, after moving out of this particular subarray, we'll try to check if the second smallest element exists or not. So if it is not the int max value, we'll calculate the sum, which would be max of max sum and the sum of the smallest and second smallest. So here we need to take the max sum value, which would be initially -1, and finally we'll return the max sum. So let's try to compile this. It's working, so let's submit. As you can see, this problem gives us time limit exceeded, as the time complexity of this goes O of n squared to calculate all the subarrays, and the space complexity would be O of 1. So we have achieved our time expected space complexity, but we need to optimize our time complexity from O of n square to O of n. So the brute force approach has a time complexity of O of n square because we generate every subarray, and within each subarray we calculated the smallest and second smallest, and we checked each element. So while this works for smaller arrays, it becomes inefficient for larger arrays. Hence gave us time limit exceeded while submitting this particular solution. So let's try to optimize this solution. So the key observation here would be that we don't need to generate all these subarrays to get the two smallest element. Instead, we can traverse through this array just once, and for every pair of adjacent elements, we'll directly consider the smallest and second smallest values, and parallelly we'll calculate the maximum out of it by taking the sum of those two elements. So here will be the step-by-step approach. So as we traverse for the array, for each adjacent elements array of I and array of I plus 1, we check which one is the smallest and which one is the second smallest. And next, we'll compute the sum of these two smallest elements from each adjacent pair, and we'll update our maximum sum. So in this way, in just one traversal, we can find out the maximum sum of the smallest and the second smallest element by taking the pair of these two elements. So let's try to dry run this. So here our first pair would be 4 and 3. So from this particular pair, we can say that the smallest element is 3 and second smallest element is 4. And the sum here would be 7, and our max sum would be updated to the max of -1 and 7, which would be 7. So our next pair would be 3, 1, and here smallest would be 1, second smallest would be 3, sum would be 4, and the max remains same as the max of 4 and 7 is 7. And next pair is 1, 5, where the smallest is 1 and second smallest is 5, sum would be 6, and the max remains same as the maximum of 6 and 7 is 7. So our next pair is 5, 6, where the smallest is 5 and second smallest is 6, and the sum would be level, and maximum gets updated as the maximum of 7 on level would be level. So in this way, after considering all these particular pairs and adjacent elements, we have calculated sum parallelly, and finally we have updated our maximum, and in this case our answer would be level. So the time complexity of this approach would be O of n, as we are traversing over the array only once, and space complexity would be O of 1. So in this way, we have optimized our time complexity and space complexity as well, and we have tackled this problem in our expected time complexity and space complexity. So let's move on to the code and let's submit it. So here one base case we can handle here would be if the size of the array, which is n, is less than 2, we can directly return -1 from there. We'll traverse over this array, and since we need two values at a time, we'll traverse through n-1 itself, and we'll grab these two values, which is smallest, which would be minimum of array of I and array of I plus 1, and second smallest would be the maximum of array of I and array of I plus 1. So after grabbing these two values, we'll update the maximum of maximum, and the sum of smallest and second smallest value. So in this way, in just one pass, we'll calculate our maximum value, and finally we'll return our maximum from this main function. So let's try to compile and run this. So let's try to submit it. As you can see, this problem got solved successfully. So in summary, the brute force approach works but isn't efficient for larger arrays, and the optimized approach reduces the time complexity to O of n by considering only adjacent elements instead of creating all those subarray values as potential candidates for two smallest elements. So that's how you solve the two smallest in every subarray. So if you found this video helpful, don't forget to like, subscribe and hit that notification bell so that you never miss an update. Drop a comment if you have any questions and I'll be happy to help. Thank you for watching and see you in the next video.